A really useful application to tangent planes to curves is to calculate linear approximations. You might have heard about one of the most famous linear approximations that some people really believe in, which is that the Earth is flat. And if you look locally within your street or up to a few kilometers, this is actually a very good approximation. If we take a tangent plane to a specific point on the surface of the non-flat Earth, it is very flat, and the approximation works really well. Other applications include, for example, video games, or sometimes when you want to study specific functions that are very complex to model, but by doing linear approximations, you reduce the problem to something which is much simpler. If you remember from a previous video and section, we were able to write down an equation for a tangent plane that was written as z equals the value of the function at a point plus the partial derivative fx at point x0, y0 times x minus x0 plus fy x0, y0 times y minus y0. And in section 10.2 in your lecture notes, what we also discussed is that this is also equal to a linear approximation that can be given in coordinates x, y. In other words, if you find a tangent plane to a surface at a specific point, as long as you keep to the vicinity of that surface, this function, which is a function of x and y, will approximate your surface quite well. What does this imply? Very simply, that if you have some function that depends on x and y as z, as long as you're in the vicinity of points x0, y0, then fxy is very well approximated by the linear approximation, which can be written as the tangent plane. There's nothing like an example, obviously, to understand how to do it in practice, but this also implies that if you're asked to calculate the linear approximation of a given surface at a specific point, what you're really doing is calculating the tangent plane to that specific surface, but usually describing it in a way that can be applied in the vicinity, not just at the specific point, but in the vicinity of that point. Let's try to do it. You'll be able to find this example. This is in section 10.2. We want to find the linear approximation to the function z equals 3 plus x squared over 16 plus y squared over 9. And we want to find this linear approximation Lxy at point given by x, y equals to -4 and 3. These are our x0, y0. And we want an approximation that will be obviously valid at the point, but also in the vicinity. Because getting a linear approximation is the same as getting the tangent plane, what we need to do is follow the same procedure as before. The first step is we calculate the value of the function at that point. In this case, we're calculating the value of the function at -4, 3. And this is equal to 5. This is the first ingredient that we'll need. It'll be 5. The second ingredients are all to do with calculating the partial derivatives. In this case, and for fx, this is a constant you don't care about. Same thing here, and it just becomes 2, which you can divide, and you can write it as x over 8. And specifically at the point of interest, it's -4, 3. This just becomes -1.5. Finally, for the partial derivative in respect to y, you follow similar procedure. You get 2 over 9y, and at point -4, 3, this just becomes 6 over 9, or 2 over 3. Once you do this, you have all the ingredients you need to calculate the linear approximation. We already know that this is 5. Here you're going to be plugging in minus 1.5. Here you plug in 2/3, and here you're plugging in the points. And this means you can write this finally as L xy of 5 minus 1.5 x minus minus, that gives you a plus, and then plus 2/3 of y minus 3. And you can also write this as 5 minus 1.5 x minus 2 plus 2/3 y minus 2. And you'll see that these terms will end up being just 1, and you can write it as 1.5 x plus 2/3 y plus 1. And this would be the equation for your linear approximation to this function. And this should definitely be valid in the vicinity of point -4, 3. If you go really beyond that point, then you'll get a very bad approximation, such as saying that the Earth is flat when you start going from one pole to the other, and it's definitely not. And you'll see that in lecture notes I also left it in this notation. Sometimes it is useful to have it like this, and other times it is more useful to further simplify it. In the lecture notes you can also see this, which is showing you the surface that's given by z equals 3 plus x squared over 16 plus y squared over 9, and also the tangent plane that we just determined, and how it is a relatively good approximation within the vicinity of -4, 3, but that once you go beyond that point, it becomes a very, very bad approximation. And this means you have a new tool of how to calculate linear approximations to surfaces and to understand how useful they can be. And therefore, we are ready to go into the very final topic of Physics 101, which is directional derivatives.